Hi, in this lesson I'd like to demonstrate graphing guidelines. In section 4.3 on page 272, there are these 9 guidelines for making a complete graph using calculus. So let me show you an example. Let's do number 15, and the function is f of x equals x squared over x minus 2. All right, let me follow the guidelines. Number 1, identify the domain. So here we see that the domain is all good except where x equals 2. That's not okay. So it's all real x such that x is not equal to 2. All right, second item on the list. Is there any symmetry? Well, I see that we have x squared would be even and x to the 1 power would be odd, but in combination, this is neither even nor odd. You could also see this by putting in positive 1 and compare it with what you get if you put in negative 1, and there's no symmetry. So we have neither even nor odd. Let's see what item 3 is. First and second derivatives. Okay, so I've got some work to do here. So the first derivative is the quotient rule. So derivative of the top times the bottom minus the top times derivative of the bottom over bottom squared. Okay, so that's 2x squared minus x squared minus 4x over x minus 2 squared, and that simplifies to x squared minus 4x over x minus 2 squared. And I can see that I might like to have a factored version of this. If I factor the numerator, I can factor out x. That's x times x minus 4 over the denominator. Okay, second derivative. So I'm going to start with this first derivative here, and I have derivative of the top, 2x minus 4, times the bottom, minus the top, times derivative of the bottom, and all of that over the bottom squared. So that's x minus 2 quantity squared, squared again. Okay, let me simplify this. So I've got x minus 2 squared. One of those is going to cancel against one of those and one of those over there. All right, now I can say FOIL this, so that's 2x squared minus 4x minus 8x and plus 8. So I just FOIL that piece. The piece over here is going to be minus 2x squared, and looks like plus 8x. And this is all over this denominator, x minus 2 cubed. So a bunch of things cancel here. The 2x squareds cancel, the 8x cancels, and I'm left with 8 over x minus 2 cubed. Okay, so I figured out the first and second derivatives. Now, 4 is critical points and inflection points. So the way that I like to do this is to start my graph on a separate sheet of paper, really big. And underneath the graph, I make a number line. And on the top of this number line, I put some marks that have to do with the first derivative, And on the underneath of the number line, I make some marks that have to do with the second derivative. So this is my step 4 for finding the critical points and the possible inflection points, and also some of the other steps. So looking at my previous work, here is the first derivative in a factored form. And I believe that the places where this will be 0 will be x equals 0 and x equals 4. So we say f prime is 0 at x equals 0, x equals 4, and f prime is undefined at x equals 2, because that would make the denominator 0. So I've got these 3 points of interest, critical points, 0, 4, and 2 on the x-axis, and that's for the first derivative. Now, watch what I do. I go to my graph, and I put an upward tick mark, upward meaning for the first derivative on the upper side of my number line, for each of these points that I just identified. So here's the point 0, and you see I line up with my graph above. Here's the point at x equals 2, 3, 4, and here's the point at x equals 4. All right, now what about my second derivative? Let's see, here's the second derivative. So the second derivative is undefined at x equals 2, and it's not 0 anywhere. So I just need to put in a tick mark facing downward here, meaning it has to do with the second derivative, and that's where the second derivative is undefined. All right, now step 5 in the process says find intervals on which the function is increasing, decreasing, and concave up, down. What that means is I need to find where the first derivative is positive or negative, and where the second derivative is positive or negative. So let's do those things one at a time. So if I can look at my formula and graph a number line at the same time, I see that the first derivative, if I have, say, negative, very negative numbers, I'll have a negative times a negative, which is a positive. And in the denominator, that's squared, so that's a positive. So for negative numbers that are very, actually any negative number, everything will be positive for the first derivative. So in this interval, between my tick mark here and going to the left to negative infinity, I have a positive first derivative, and I indicate it by putting a positive sign there. Now, the next interval of interest is between x equals 0 and 2. So if I try out a trial number, say, in there where x is 1, I see 1 is positive. This term, 1 minus 4, is negative. A positive times a negative, denominator is always positive, leaves me with a negative. So in here I put a negative symbol to indicate the first derivative is negative. Continuing on, between 2 and 4, I see that if I say put in 3, 3 is positive, 3 minus 4 is negative. I still get negative in that region, so I put a negative sign there. Finally, to the right, if I put in very positive numbers, everything in the first derivative is positive, giving a positive result. So these positives and negatives indicate the slope, whether the function's increasing or decreasing. So I can put a little reminder here that this means the function is increasing there, decreasing here, and increasing here. Those are my increasing, decreasing slopes. Next, I want to do this similar analysis for the second derivative. And here I see that the second derivative is a cube of x minus 2. Well, let's just try this out. So if x is less than 2, say it's 0, I have a a negative result. 8 divided by a negative to an odd power gives me a negative result. So let me put in a negative for that. And then to the right of 2, my second derivative would be everything's positive. So I'll put in a positive here. So these negative and positive indicates concavity. Concave up or concave down. Negative is concave down. That's where the cave opens downward. Positive is concave up, where the cave opens upward. So that's the type of curvature we have. Now let's check in with a list here, looking back in the textbook. Identify extreme values and inflection points. And this is step 6. And then step 7, locate vertical, horizontal asymptotes and determine end behavior. And I will add in here that I like to, at this point, plot any points that I can plot easily. So let me write down the original function that we have here. We're working with f of x equals x squared over x minus 2. So here I see a increasing followed by a decreasing. I'd like to know the value at this point where x is 0. When I plug in x is 0, I get 0 over negative 2. So here's a point on the graph. What happens at the next interesting point here where x is 2? Well, when x is 2, I have a 0 denominator, and approaching from the left, I would have like 1.9 minus 2 in the denominator. So that's going to be a negative infinity type of situation. So I have an asymptote here. Now, going back to my previous point, increasing, decreasing slope touching this point means I'm going to have a little local maximum there. So I like to draw a little curve there just to remind myself that I'm going to have that type of concave down maximum at that point. Let me draw my asymptote upward as well. Now, going to the right of x equal 2, I still have a negative slope. Let's see how this is going to work. But instead of just being a little bit underneath 2, I'm a little bit above 2. Imagine 2.1 minus 2. And so I see that I have the denominators approaching 0 as I go to 2, so I'll have an asymptote. But this time it's positive infinity instead of negative infinity. So I'm going to have some kind of thing going up here. All right. I might even put a little mark there to remind myself. And then finally, let me look at this point where x is 4. So I can compute, let me do it down here, f at 4 is 16 divided by 2, so that's 8. So at 4, I have a point 1, 2, 3, 4, 5, 6, 7, 8. I have a point right here. Now, is that what kind of point is it? Asymptote, maximum, minimum? Well, we have to look at the number line with derivatives here. So I'm decreasing and then increasing. It looks like this is a minimum right here. Let's check the concavity. Concave up, curved up with the cupping upward. So yeah, I can put a little cup symbol here. This is definitely a minimum. So now I'm ready to actually graph the function. There is step 8 said find the intercepts, and I think we've already done that. Right here is the only intercept. An intercept, of course, is where the function value equals 0, which is when x equals 0, or other way around, when x equals 0. So this happens to be a 0, 0 intercept for both x and y. So other than that, I'm ready to actually graph the function. I've got all the information coded here, and I'm coming up with a positive slope here to this maximum, and then going down to an asymptote. And on the right side of the asymptote, I'm coming up from positive infinity and going back up. So my function must be something like this. And there you have it. graphing a function according to the graphing guidelines on page 272.